All right, recording and re-rolling. You guys got this page out from yesterday. We did about half these yesterday. We're gonna knock out the rest right here. So one of the last ones we did yesterday, number 4, was mass energy equivalent. It said you have some mass. Let's say you convert that completely into energy by a nuclear reaction, or the change of mass, right? Then how much energy does that represent? Okay. Now the first one we're gonna tackle today starts out that way, and then yeah, right. And then there's an extension question, which is how long would that energy last? Right. So there's a dimensional analysis half to this too. All right. So right now my numbers are different than your numbers. That's good. That's gonna be the same process. Right. So let's follow the story. Say you're a resident of a spaceship moving between stars in a galaxy. In order to sustain decent standard of living, every resident of the spaceship consumes an average of so many kilowatt hours of energy per day. Mine says 35. Yours might say something slightly different than that, but that's pretty much a developed world standard. Now that energy, like right now, we're all consuming energy, not just uh, the lights and the air conditioning and driving in our vehicles around town, but also like every time you buy a product off the shelf at the store, right? There's a certain amount of energy that went into delivering that product. Okay, so that's all I can bet in this number, and let's say we're going to take that into space. Okay. If the ship's fuel storage contains a given amount of nuclear fuel, let's say 100% convert into energy, maybe it's like antimatter or something, for example, per resident, how long can a ship go before having to refuel? So let me pick a number like, here we go. Pick this number. Okay. So mine says 0.05 kilograms. Now, pause here. Guys, 0.05 kilograms. How many grams is that? Kilo, how many decimal places? 3 decimal places? Kilo is 1,000. This is like 50 grams, 50 grams. Here's a 50-gram lab mass. Okay. So what if I just had this as my fuel and I'm converting this completely into energy, right? So maybe like with antimatter, for example. Okay. And I'm using energy at the same rate that we're using it in a developed country. How long is it going to last? So this is going to be 2 parts. So follow along with me here. The first part is mass energy equivalence. E equals mc squared. The amount of energy depends on how much mass. So I'm going to take my 0.05 kilograms. I'm going to multiply by 3 times 10 to the 8 meters per second, and that's being squared. Okay? And I'm going to get some number of joules out of this. So I'll do this. You guys do this. 0.05 times 3 times 10 to the 8 being squared. And that is 4.5 times 10 to the 15, and that's joules. Okay? Joules. Right, you guys good? Right. And you guys got a number it's probably something like 10 to the 15 joules or something like that. Now, we did do something like that yesterday, but I want to take this one more step. And I've got a dimensional analysis table. Say, if we use energy at some rate, right, how long will that energy then last? And I did put it in kilowatt hours. That's just a common way to represent energy, like from a power company, because kilowatts is power and hours is time. So power times time would bring you back to an energy unit. So let's go 4.5 times 10 to the 15 joules. Right? I know on the table says joules per person or something, but let's just think for a single person. Okay. And I'm going 35 kilowatt hours per person per day. Again, I'll just leave out the person, just do like per day. Right? So I got an energy unit here and a different energy unit here. So the energy cancels out, right? But okay, and I'm going to have like some number of days left on the board. Right? But I need to reconcile these units right now just to move things along a bit. I know we're getting closer to the end of class. Right? I put it in the table anyway. I know that there are 1,000 joules per second in every 1 kilowatt. So that's exactly in the table. Okay. I also know that there are 3,600 seconds in 1 hour. So I'm really helping you guys out a lot with this table because you guys see seconds and seconds cancels, joules and joules cancels, hours and hours cancels, and kilowatts and kilowatts. Okay. So the only unit on the board is days. Okay. So how many days is this going to last me? You guys get that concept? How many days? So we're just going to multiply across the top, and there's only one number at the top, and then divide by all the numbers at the bottom. And that'll tell us how many days. Let's find out. What is 4.5 times 10 to the 15 joules, close parenthesis, divide by, open parenthesis, and then all these numbers, 35, 1,000, 3,600. Okay? And I'm getting a crazy big number. I'm getting like 35 million some days I should have thrown in one more step, which I'll just do right now anyway. How many years would that be? Guys, how many days in a year? 365. So what if I divide this by 365? Right, that's telling me 97,000 some years. Woo! So wait, is that? Yeah, okay, there you go. Okay. So this right here, if I were to convert this completely into energy and use energy at the rate that I'm just use in my daily life, it would last me like almost 100,000 years. Okay, you guys get that? Okay, everybody good? Okay. Now the rest of these, okay. Okay. Number 7, as you speed up and approach the speed of light, your length is seen by a non-accelerating observer. Let's check out this length dilation. Okay. So uh, if you approach the speed of light, isn't this v approaching the c? Right? So we got a good sized fraction here. 1 minus the fraction is still a fraction. So this is between 0 and 1. Square root of anything between 0 and 1, still bounded between 0 and 1. This whole Lorentz factor is bounded between 0 and 1. So guys, if you start off with like 10 meters and you multiply by something between 0 and 1, do you get something that's longer or shorter? Shorter. Right? Shouldn't that be the answer? Right? You guys got that? You guys got that? Right? Like the train going through the tunnel yesterday, or if you throw a spear through a pipe and you're in the pipe's frame of reference, it's all the same thing. Right? Number 8, as you speed up and approach the speed of light, your mass is seen by a non-accelerating observer. Check out. Well, okay, I've got momentum here. I said mass a few years ago, but I think it's better to say momentum. But it's the same idea. Because this is Large Hadron Collider. Large Hadron Collider, particle physicists speed up protons near the speed of light. Right? When they see that, let's say they put in like a gram of protons and they speed them up and say, whoa, there's what, less mass or more mass that appears to manifest? More. In fact, if it's like 99.9 something percent of speed of light, it's actually approaching infinity. Right? So if they put in 1 gram of material, they might have like 20 grams appear to be moving around that they have to push into a circle. Okay? Number 9, in a nuclear reaction, which of the following is taking place? Guys, what is the interpretation of E equals mc squared? E equals mc squared. What does the E stand for? Energy. What does the M stand for? Mass. Didn't today, we solve a problem like turning this mass into energy? Isn't that what's going on in a nuclear reaction? Right? You guys follow that? Okay. Now, number 10, 11, I may reverse these on your paper, but it might be 11 and 10. You guys get the idea. Using the time dilation equation, solve for t when speed equals about 0 meters per second. Okay? This is that correspondence principle that I've been telling you guys about throughout the Kahoot. Okay? That's to say, what if you are not moving even at a relativistic speed, as we are not right now? Right? We're all just like sitting in front of each other, right? So let's plug in 0 for this v and see what happens. Guys, what is 0 divided by c? 0, and that square is still 0. What's 1 minus 0? 1. What is the square root of 1? 1. What is t naught divided by 1? T naught. Oh, look at there. T equals t naught. That's to say that we all agree on how much time has passed, right? Again, like the fastest any human has moved is probably like going to the moon, I'm imagining, something like that. If you plug in the escape speed of Earth here, that's still approximately 0 for this, and then you still get the same approximation. Okay? That's correspondence principle. So Einstein physics does agree with Newtonian physics, right? As long as you're non-relativistic scenario. Okay, and last one that we haven't done yet. Okay, so let's close out this paper, but there's the back half of this paper we're going to do another day. In the mass dilation, or I might have been teaching at momentum dilation, similar idea. What happens to the perceived mass as v approaches the speed of light? Ooh, hey, now we're back at the Large Hadron Collider. Guys, Large Hadron Collider, we're speeding up these particles near the speed of light. So as you approach the speed of light, what happens to the momentum or perceived mass? It goes up towards what? Yeah, right? Because isn't there the vertical asymptote right there? That would have to be the case, right? You guys see that? Okay. And if you were to reach the speed of light, then your mass would appear to go infinite. Like a boundary condition that you'll never reach. All right. So you guys good? Good? All right, so hang on to that page because gonna do something with the back after that another day. All right. Oh, just in time too. All right, so that's a wrap on today.